All right, we have hypothesis testing. We're going to test two means with hypothesis testing. Then we have some linear correlation that we're going to do also, just taking a look at two different variables and trying to come up with an equation that relates two variables to each other. And those are the last things that we are going to cover. So I'm going to try to cover both things today with testing two hypotheses, one a z-test and one a t-test. That gives us a little leeway tomorrow because some of you are not going to be here. So I'm trying to get through as much information as possible today. Tomorrow we'll be able to work on worksheets from today and also tomorrow with respect to homework if I can get everything accomplished here. So that gives us no homework on to work on tomorrow. We'll just be working in class on what we're talking about today. Monday and Tuesday next week, we'll take a look at, like once again, linear relationships between two variables. And pretty much at that point, we are done with the class. New material. We'll do one last final unit test. Then we have a project to do, and then we have a final. And that's it. So, and the project is basically probably about a 2-day project. It's sort of like the M&M project in regards to the amount of time it takes. You're going to be doing a survey, gathering data, calculating all your statistical analysis, and doing hypothesis testing on your data. So it's going to be everything that you put together, and then we'll have a final. Our final in here, seniors, you have to take the final early. Underclassmen, we're going to all be taking it at the same time. So we don't have the finals week that we have to do anything. We'll have everything taken care of before that. So that's the 2.5 weeks that we have left here. We'll go really quick. Today we're going to start, we're going to talk about hypothesis testing of two different means. We're going to compare two different means. We'll talk about the ACT score between males and females. You could take a look at salaries or household incomes between two different communities and compare household incomes between two different communities. There's studies that are out there right now that are wages for different genders, okay, and making a comparison of wages of different genders that are out there and how males tend to get paid more than females, and they have these comparisons that are sitting there, and they did all this data analysis in regards to that. So there's a lot of comparison that goes on in regards to, once again, males, females, communities to communities, nation to nation, comparing this nation to this nation. So, ACT scores of United States students compared to ACT scores for English students or standardized testing for English people in England. So there's ways of being able to test these with hypothesis testing in regards to comparison of means. The nice thing about this is what basically your null and alternate hypothesis will be one of these three. You have two different means that you're comparing, mu1 and mu2. You have two different groups of people. You're comparing group 1 to group 2. These two values are going to be equal or not equal to, or one's going to be greater than the other one. The household income in Downton compared to the household income, average household income in Orville. Which one is greater? Okay, the household income in Downton compared to the household income, average household income in Worcester, the higher end people, the hoity-toities a little bit. The people that live in Worcester, well, they sort of hold themselves a little bit higher standard over there. Just my 59 years of living, I've sort of noticed that a little bit living in Wayne County. You have communities, okay, community of Downton compared to the community of Jackson down over there, over Massillon. What is that average household incomes? Compare those two. So, but we can make comparison between the means. The nice thing about this is you have two groups of people, or two groups. These two values will be equal or not equal to. One will be less than, or one will be greater than the other one. So this is going to be your null and alternate hypothesis. Okay? It will be a null and alternate hypothesis. You don't have to throw numbers in there at all. You're just comparing the population means of two groups. Whether it's male or female, whether it's genders, your comparison of two values. And once again, this is what you're going to have. What you have to signify what you need to signify is what is group 1 and what is group 2. You have to signify, you have to denote, this is my group 1, this is my group 2. It's going to look very similar to what we just did. It's going to be, if we have populations or sample sizes that are greater than 30, we're still going to be using z-tests. If we have sample sizes that are less than 30, we're going to be using t-tests. We're still going to be doing a bell-shaped curve. We're still going to be able to pull critical values from a t-table. Okay? All the process is exactly the same, except for one thing: how we calculate the z-test value. Our z-test value. We have sample mean 1 minus sample mean 2, minus mu1 minus mu2. And this is over a sigma x1 minus x2. And how we calculate this will be over here to the right. It's your variance 1 divided by sample size 1 plus variance 2 divided by sample size 2. And you take the square root of that. Now, once again, these are things I'm not going to ask you to memorize. This right here, you have room at the bottom of your t-table, down here at the bottom. On your chi-squared over here, you already have your chi-squared stuff that we talked about before, your alpha divided by 2 on your chi-squared table. On your t-table at the bottom here, or at the top, it doesn't matter. You can type in, or you can write in, your z-test is x bar 1 minus x bar 2 quantity minus mu1 minus mu2 quantity divided by sigma 1 x1 x minus x2. And you can put this over here, your sigma x1 minus x2 is that over there. Okay, so you do not have to memorize this. If I'm doing a mathematical problem or I'm doing something, and I'm looking to solve compare two means and hypothesis testing, I'm looking this up. I've taught math quite a few years, taught stats quite a few years. This is something, it's almost like Christmas. It's a surprise every time I open it up because I don't remember. I'll remember this for a little bit of time now because we're going to do it a few times and I'll remember it. But leading into today, I couldn't, if you would have asked me how do you calculate your test value for two means, I would have said, I'm not quite sure. Let me open this up and delete the rectangle. and I'll tell you how to do it then. So it's something I don't expect you to memorize and have memorized. If you're going to be a part of a math career that's going to involve higher level statistics, you're going to have to know this. But if you get into an actuary world, an applied science world, and you actually get a job doing and working with this, okay, bless you, all you're going to have to do is clickety-clack into a computer, what's your X bar 1, what's your X bar 2, what's those equal, what's your mu 1, mu 2, and what your sigmas, your 2 sigmas, and what your sample size is. And it will do all the calculations for you. Very similar to what your calculator does. And once again, if the sigmas are not known, you can use samples. Because once again, mathematicians, applied mathematics, statisticians, all statisticians are looking for are numbers that they can work with. They want to get an approximation. It may not be exact, but they don't live in the exact world. The only thing that they live in with respect to an exact world, those statisticians, is making sure their paycheck is correct. If they're $5 off my paycheck, hey, what? I'm sorry, why is my $5? Why is my paycheck $5 less than what it was before? Okay, they're worried about that. But with respect to making judgments in regards to statistics, they're okay with, okay, it's close enough. Once again, don't be messing with their paycheck though. Mean ACT score, 43 males. High school students is 21.1. Standard deviation of 5. Mean ACT score, 56 female students is 20.9. Standard deviation 4.7. Alpha value point was 0.1. Can you reject a claim that male and female students have equal ACT scores? Okay, we're making comparison between males and females' ACT scores. Is there a difference? Okay, you can also talk about in regards to race. Okay, the race. So we can compare ACT scores of different races in the world. Okay, or in the United States. Is there a difference between them? And there's a lot of people, there's a lot of groups out there that do these studies. Okay? They do these studies. Okay, so what you have to categorize is what is group 1 and group 2 for you. To me, I keep it simple as possible in my brain. Whatever group comes first in the problem is my group 1. Why? Because they came first. Whatever group comes second in my problem, I'm putting as group number 2. Okay, so if I look here, I have 43 males. That's my first group. So my group 1, I got my sample size, N1 is 43. Their mean score, X bar 1, is 21.1. Their standard deviation, S1, is the value of 5. What comes second in my problem is females. So I have group 2. So I have group 1 is my males, group 2 is my female. I have 56 females, so N2 is 56. Their X bar is 20.9, and their standard deviation is 4.7. Null and alternate hypothesis. I could have done that first, doesn't matter. We're testing to see, is there a difference? Not if one is greater than the other, just is there a difference between them? Or can we pretty much say they're the same? So if I take a look at my null and alternate hypothesis, are we going to talk about equal to, not equal to, or less than or greater than? Equal to, not equal to. Okay? Equal to, not equal to. Once again, equality always goes with the null hypothesis. So we have mu1 equal to mu2 and mu1 not equal to mu2. Okay? One tail or two tail, Brendan? Two tail. So we have a two tail test. Got my bell-shaped curve here. We are looking at a two-tail test. Okay, should look very familiar to what we talked about before. We have an alpha value of 0.01. So I go to my t-table, alpha two-tail test. So I look along the two-tail row there, my alpha value of 0.01. My sample sizes are 43 and 56, so I got bigger than 30. So I can drop my 0.01 all the way down to the bottom. 2.576 and negative 2.576. Once again, nothing different here. Okay, this looks almost familiar, except for now we're talking about two different groups. Okay, so we have our z-test. X bar 1 minus x bar 2 minus mu1 minus mu2, all divided by the sigma x1 minus x2. Now the question is, how do I evaluate this? We're given x1, x bar 1, x bar 2. But the second group here, we have mu1 minus mu2. We're not given any population means. But if we take a look at our null hypothesis, in our null hypothesis, we are assuming mu1 is equal to mu2. Well, if mu1 is equal to mu2 and I subtract two values that are equal, what do we get? 0. We get 0. So this value here goes to 0. Why? Because in our null hypothesis, we are saying they're equal. Now, once again, when you get into, if you get into stats beyond stats 1, you'll get into problems where mu1 is not going to be equal to mu2. But for our purposes, mu1 is equal to mu2. Even if this was less than or equal to or greater than or equal to, our null hypothesis here involves the idea of equality. And the null hypothesis is something that we sort of assume to be true. The alternate hypothesis is the thing that we sort of hope is true. So we are assuming that there's a possibility with our null hypothesis that we have equality there. Once again, if they're not quite equal for statisticians, that's okay. So what we're left with is, let's see, x bar 1, which is 21.1 minus x bar 2, 20.9, minus this value is 0. Now what we have to determine is this denominator, which is S1 squared over N1 plus S2 squared over N2. Once again, if I have sigma, I use sigma. If I have sample, I use sample. It's okay. So now we get to have a KYC moment. Know your calculator. Let's see. We have square root 5 squared divided by 43 plus 4.7 squared divided by 56. What you're able to do is type that straight into your calculator. So you can go second square root 5 squared divided by 43 plus bless you. .7 squared divided by 56. Close your parenthesis out. Your calculator will follow orders of operations. Hit enter. We get 0.987. And once again, you could do this separately if you want to take 5 squared divided by 43 and add to that 4.7 squared divided by 56. Oopsie. You get a value, then you take the square root of that answer. Oopsie. Okay, now hold that in your calculator. Don't clear that out because we had to take our numerator and divide by that. So our numerator, quantify this. So we have quantity of 21.1 minus 20.9. And your quantity, okay, get that as a quantity, and then divide by second and your negative sign. That pulls down this answer that you just had here. Okay, so you don't have to recopy. Again, KYC, know your calculator. We get a value of 0.202. .202, which throws us right here. This is our test value. Once again, we still have non-critical and critical. So we failed to reject the null hypothesis. Of ACT means are the same for the genders. Yeah. Once again, very similar ideas to what we just did. We can also look at a t-test. When your sample sizes are less than the value of 30, your null and ultimate hypothesis is exactly the same. There's nothing different there. But what occurs with a t-test is we had to worry about a degree of freedom to find these critical values. That's what changed before when we were doing hypothesis testing in the last section. Okay, we had to use our degree of freedom to find our values over here. Well, the problem we run into now is you're going to have 2 degrees of freedoms. Which one do we use? Our test value is still the same. To find critical values, you take the smaller of the sample sizes to determine the degree of freedom and your critical values. You look at your smaller sample size and you pull your critical values from there. To find this denominator here, it is the same as the z-test when it's denoted the population variances are unequal. When your population variances are unequal, and they will state this within the problem. When the population variances are unequal, you do the exact same thing as you just did with the z-test. Once again, the only thing that is different is finding those critical values. When the population variances are equal, this turns into a little bit uglier thing to work with. We're just going to address it. When you have a problem on a test, it's going to be the population variances are unequal. When the population variances are equal, you have this sigma hat, square root of 1 over n1 plus 1 over n2. How we calculate the sigma hat? We have this equation, but this also reduces down to square root of degree of freedom 1 times your variance 1 plus my degree of freedom 2 times my second variance, and this is over the degree of freedom 1 plus my degree of freedom 2. This also puts it into that mode. They are the same. Because how I calculate my degree of freedom is N1 minus 1 and N2 minus 1. Well, N1 minus 1 plus N2 minus 1 goes to N1 plus N2 minus 2. This gives us this sigma hat that we have to multiply by 1 over N1 plus 1 over N2. I like looking at degree of freedoms. In a textbook or in a formula sheet, they'll give you this. I like this because this is a little bit cleaner to me. I can find my degree of freedom and do a little bit of mental math to be able to do that because I'm only subtracting 1. It's not like it's a higher level mathematics. Population variances, once again, you only use that sigma hat when the population variances are equal. So if we just take a look very quickly, here's one where your population variances are equal. Once again, I take a look at what comes first. Males come first. So N1 is 12, and DF1 is 1 less than that, 11. We're doing the exact same information here. X bar 1 is 21.1. S1 is a value of 5. And then we have N2 is 15. DF2 is 14. X bar 2, 20.9, and S2 is 4.7. Null and alternate. Can you reject a claim that male and female students have equal ACT scores? So we're still mu1 equal mu2, mu1 not equal to mu2. We're still a two-tail test. Still two-tail test. But now to find our critical values, we look at our degree of freedom. Our degree of freedoms are 11 and 14. So to find my critical values, I'm going to use the smaller of those critical value or degree of freedom. So I'm going to use the value of 11. And since they are unequal, that's where we're going to have to use our sigma hat. Once again, that's where it gets, this is probably one of the more complicated calculations of stats 1. Where we have that sigma hat. We have degree of freedom 1 times S1 squared plus dF2 times S2 squared over degree of freedom 1 plus the degree of freedom 2. If you want to use ends, that is fine. If you want to use ends, that is fine. So we have a square root of 11 times S1 squared, 5 squared, plus degree of freedom 2, 14, times 4.7 squared over 11 plus 14. This gives us sigma hat. And then we have to multiply that times, oh my. Well, it was last period. They're not running it now, so. Tomorrow, once again, will be a work day. We'll finish this problem tomorrow. We'll go through some calculations. But will be a work day. The 2 worksheets we have is for today and tomorrow both. Adios, have a good day. There they are. There it is.